Hi, in this video, we are going to continue our course on complex numbers and polynomials. So, complex numbers and polynomials are an important part of our polynomial course, and we are going to look at some of the properties of complex numbers using certain problems. So, the first thing that I want to do here is talk about this particular property of conjugate complex numbers. So, let p of x be a polynomial like this, a d x bar d, so on till a naught. Now here, this complex number has this polynomial has real coefficients. So that means that all the numbers ad minus 1 till a naught belong to the set of real numbers, right? Now we know the property that real numbers, if you try to take a conjugate of a real number, it is equal to the same number, because real numbers are on the real axis of the number line, and the conjugate of a real number is itself. Right? So this is a plus 0i, and the conjugate of this is equal to a, right? So because of that, we get this important connection. So let's say we write this in terms of z, and we write it as ad z bar d plus ad minus 1 z bar d minus 1, and so on till a naught. This is my complex polynomial pz. Here z can be a complex number. If you calculate pz conjugate, what will that be? It will be ad z conjugate power d plus ad minus 1 z conjugate power d minus 1, and so on till a naught, right? So if you think about this, this basically can be combined and written as ad z bar d plus ad z bar d minus 1, and the whole thing can be combined like this and written as a whole conjugate. That is one of the properties of conjugates, right? So what we can write this as is p of z whole conjugate. So p of z conjugate is p of z whole conjugate, right? And because of this fact, what we can say is if you multiply p of z with p of z conjugate, you will get something like this: p of z multiplied by p of z whole conjugate, which will be the modulus of p of z whole square. Because p of z is a complex number now, and p of z times p of z whole conjugate will give you the modulus of p of z whole square. This is a very important property which we will see when we try to solve a few problems. Keep this in mind. This is a property which connects conjugation to polynomials. So let's look at a sample example. This is example 1. Let w be minus half plus I root 3 by 2. Basically, w is a cube root of unity, and p of x be the polynomial ax minus b, right? I want to show you what happens if you do p of w times p of w conjugate, right? So let's see what happens there. So p of w is obviously aw minus b, and p of w conjugate is aw conjugate minus b. So when we multiply these two things, what do we get here? We get aw minus b times aw conjugate minus b, which becomes a square w conjugate, and then we have minus abw minus abw conjugate plus b square. Now think about it. What is w conjugate? W conjugate is equal to w square. This is a property of cube roots of unity. So w conjugate is w times w square, which is w cube, which is 1, because this is a cube root of unity. So this is becoming basically pw times pw conjugate is becoming, this part is 1. So it is a square into 1 minus ab w plus w conjugate plus b square. And that can be written as a square. Think about what is w plus w conjugate. So this is w plus w square, which is equal to minus 1, because the sum of the roots of the three cube roots of unity adds up to 0, right? So what we are getting here is -1 in this part. So we get a square plus ab plus b square, right? So this is a result that will come in handy later. So right now, just keep in mind, we had a linear polynomial like this, and we took PW and PW conjugate product, and what we got was a square plus AB plus B square, right? Which is like saying mod of PW whole square. How? Because what was PW? PW was AW minus B. So that was AW would be minus A by 2 plus I A root 3 by 2 minus B. So if I try to take a mod of this, right, and square the mod, let's calculate it on the side. We'll see what comes. We have basically PW is equal to minus A by 2 minus B plus I root 3 A by 2. So mod of PW is equal to square root of this square plus this square, right? So this will be a square plus by 4 plus b square plus 2a by 2 into b plus 3a square by 4. So see what we are getting. We are getting a square plus b square plus ab under the square root. So square of that whole square is a square plus ab plus b square. So we got the same result by actually multiplying here, and we are verifying that this result is coming true, right? So that will come in handy in the next problem itself. So let's look at the next one. This is the question. Prove the following identity. Prove the following identity. So the identity looks like this. A square plus AB plus B square multiplied by B square plus BC plus C square multiplied by C square plus AC plus A square is equal to, we have to show A square B plus B square C plus C square A whole square plus B square A plus C square B plus A square C whole square plus A square B plus B square C plus C square A times B square A plus C square B plus A square C. Now, obviously, I don't want to do pure algebra here. It will be super annoying to try to multiply this and prove that it is equal to this, right? So we have to think of some clever trick to try to get this, right? We will use the result that we got in the previous thing. So we'll define a new polynomial, find a polynomial p of t, which is equal to ta minus b, tb minus c, and tc minus a. Now, because we know from the previous case that p of w times p of w conjugate was equal to a square plus ab plus b square when p of x was ax minus b. This is the result that we just now got from the previous problem. So here, if you do p of w times p of w conjugate here, notice that all the three forms are in the same form. It is in the form of ax minus b. So it is ta minus b, tb minus c, and tc minus a. So the product here should become a square plus ab plus b square, b square plus bc plus c square, c square plus ac plus c square plus a square, right? So which is the left hand side of the thing that we want to prove, right? So basically we have gotten left hand side here is equal to p of w times p of w conjugate, right? Now actually let's see what is p of t. If you expand p of t, what do we get? P of t expansion is pretty easy to do. You just multiply everything. You get a, b, c, t, q minus, do some algebra and you will be able to verify this is a square b plus b square c plus c square a t square plus it will be b square a plus c square b plus a square c t and minus abc. This is actually my p of t, right? How did I get this expression? I have just done basic algebra on this polynomial. I have multiplied it out and I've collected all the terms in the decreasing order of powers of t, right? Now, since the LHS is P of W and multiplied by P of W conjugate, we will try to evaluate what is P of W and P of W conjugate here. So P of T I will write again A, B, C, T, Q minus A square B plus B square C plus C square A T square plus B square A plus C square B plus A square C T minus ABC. So let's find out P of W. Obviously, this becomes ABC times W cube, which is 1, minus A square T plus B square C plus C square A, this is W square, plus B square A plus C square B plus A square C W. And this is minus ABC. So notice that the ABC and the ABC get cancelled, and you have basically minus A square B plus B square C plus C square A W square plus b square a plus c square b plus a square c times w, right? This is p of w, right? Now remember the result that we got earlier. The result that we got earlier was p of w times p of w conjugate was equal to p of w mod square and was equal to a square plus ab plus b square if p of x was in the form of ax minus b. Now, I don't have to actually calculate I don't have to calculate P of W conjugate and try to actually multiply it here because I already have an expression, this expression, which will help me find mod of P of W square. I can find mod of P of W squared from here because I know that W is minus half plus I root 3 by 2 and W square is minus half minus I root 3 by 2, right? So writing this as a complex number, I will be able to calculate the mod of this. How do I do that? What I can say is, right, I will not even put this value in, I think. I will just use some properties of cube roots of unity. What I will do is I have to find out mod of P of W. So I have to find a mod of this a square b plus b square c plus c square a w square plus b square a plus c square b plus a square c w. I can take a w common, mod w is 1. So this becomes minus a square b plus b square c plus c square a w plus b square a plus c square b plus a square c. That's it, right? Now, this thing will become, this part is 1. And when you calculate the mod of this will become a square b plus b square c plus c square a whole square plus b square a plus c square b plus a square c whole square and plus a square b plus b square c plus c square a times b square a plus c square b plus a square c. How do I do that? Just think of this as x, think of this as y, and write w as this. So you have basically minus x by 2 minus root 3 by 2 x I plus y. So you have to do y minus x by 2 whole square plus 3 by 4 x square when you take the mod. So what will come out? Finally, it will be y square plus x square plus Notice that there is a minus sign here. So minus of minus half. So this is a plus half actually. And right. Okay, I'll just do it on the next screen for clarity. So what I have is modulus of b square a plus c square b plus a square c minus a square b plus b square c plus c square a times w mod square of this, right? I will call this as y and this as x, right? You have y minus x times, what is w? Minus half plus I root 3 by 2. And I have to do modulus of this square, right? So this is clearly y plus x by 2, y plus x by 2 minus I root 3 by 2x. This is my complex number. The modulus of this will be y plus x by 2 whole square plus 3 by 4x square, right? And now this is clear that this is x square plus y square plus xy. When you put back your x and y as these things, we are getting the result that mod of p of w whole square is the RHS of the thing that we wanted to prove. And the LHS we have already shown that p of w times p of w conjugate was the LHS. And since from the previous problem we know that these two things are same, we have established the proof. So notice how the previous result has come in very handy to prove this very complicated looking identity, right? So complex numbers can be useful to you in many surprising ways. And in this section of the course, we will look at several videos where I'll show you all of these kinds of tricks. So stay tuned for more and more problems like this. So the next question, let's go ahead. So question number 2. Find the complex number. Find the complex number w with modulus 1, which maximizes the modulus of z is equal to w plus 2 whole cube times w minus 3 whole square. Okay, so we have to find the complex number w with modulus 1. So we are given mod w is 1, which maximizes the modulus of this complex number, right? Let's say w was some complex number t plus I s, and keeping t and s are two real numbers, right? So we know that w conjugate would be t minus is, and w plus w conjugate would be 2t, and w plus w conjugate by 2 will be equal to t. Here t is real. So we know these facts. Now let's try to think about what is mod of w minus a whole square. By the properties of conjugate, this is w minus a times w conjugate minus a. Here a is a real number. A is real. So this calculation will become, think about it, it will become w conjugate minus a w conjugate minus a w plus a square, right? And now w conjugate is 1 because modulus of w is 1. So w conjugate is mod w square minus a common w plus w conjugate plus a square. So now mod of w minus a whole square is becoming, what is w plus w conjugate? It is 2t, because w was t plus is, so t is the real part of w. So this is 1 minus 2at plus a square, right? So keep this result in mind. We will be using this when we try to maximize the modulus here. So if you think about the mod of z right now, mod of z right now would be mod of w plus 2 whole cube times w minus 3 whole square, which is the same as saying mod of w plus 2 whole cube times mod of w minus 3 whole square, right? Now think about it. We know mod of w minus a whole square is this, where a is a real number. So using that result, what do we get? We get that w plus 2 mod this part is w plus 2 mod cube. So I need mod square. So let's calculate instead z mod z square, which is w plus 2 mod power 6, w minus 3 mod power 4, right? Now this is w plus 2 mod square whole power 3. This is w minus 3 whole square power square, right? And now I'll apply my result. W minus a mod square is this, right? So here a is obviously minus 2. So this part will become 1 minus 2. So plus 4t and plus 4 whole cube. And this part a is 3. So this becomes 1 minus 60 plus 9 whole square, right? So we are getting 5 plus 4t whole cube times 10 minus 60 whole square. That is mod z square, right? Where t is real part of w. Try to understand, we are applying this result here. A was minus 2 and then a was 3. That's how I'm getting this, right? 10 minus 60, is it coming? 2 into 3, 60, right? Correct. Fine. We have to maximize this value, right? If you want to maximize this value, let's try to think of what we can do. So our goal is to, let me clear some space here. Maximize 5 plus 40 whole cube times 10 minus 60 whole square. So by AMGM inequality, what we can say is GM here first of all, you have to realize that both these quantities are positive. Then only we can apply AMGM. Why are they positive? Because T was real part of W and mod of W was 1. Mod of W is 1. So therefore T must be less than equal to 1. Or at least the modulus of T must be less than equal to 1. Then 5 plus 40 is positive and 10 minus 40 is 10 minus 60 is also positive. Mod T is less than equal to 1 means T can be between minus 1 and 1. So in no case can these two quantities be negative. So we can apply AMGM. What we can say is the product of these 5 plus 40 whole cube times 10 minus 60 whole square. The product of this taken to the fifth root, because there are 5 terms, 3 terms here, 2 terms here, taken fifth root. So this is the GM stuff, should be less than equal to the AM of these, right? So it will be 5 plus 40 plus 5 plus 40 plus 5 plus 40 3 times plus 10 minus 60 plus 10 minus 60 divided by 5. I am taking the AMGM for 5 terms, which are 3 terms are repeated here and 2 terms are repeated here. Notice this is nice because 40, 40, 40 get cancelled with the two negative 60s and you get 15 plus 20, so 35 by 5, so this is 7. So we are getting this quantity, the fifth root of this quantity is less than equal to 7. So this is less than equal to 7 power 5, right? So this quantity was actually mod z square. So mod z square is less than equal to 7 power 5. Therefore, what we are getting is mod z is less than equal to 7 power 5 by 2, right? And the equality happens when the quantities which were being done ANGM with 5 plus 2, 5 plus 4t should be equal to 10 minus 60, right? That time the equality can happen. So this means basically that 10t is equal to 5 or t is equal to half, right? So that means the real part of W must be half, and only then can you have this equality. Mod z will be equal to 7 power 5 by 2. Now notice that if the real part of W is half and the modulo of W is 1, then the complex number must be plus half plus minus I root 3 by 2. This is the complex number at which equality happens. And for any other complex number, the mod z is less than 7 power 5 by 2. So this is a sort of a tricky solution where we took advantage of, first of all, this identity that mod of W minus A whole square, where A is real, is actually coming out to be 1 plus A square minus AT. Here T is equal to, what was T? T was the real part of Z, or T was the real part of W. And we took advantage of that identity to calculate our mod of W plus 2 whole square and mod of W minus 3 whole square. And finally, when we got a product, we did ANGM, right? So a nice tricky way to solve the problem. Let's look at the next one. In this question, we have to find all complex numbers with modulus 1 such that summation k goes from 1 to 1006 z mod of z to the power 2k plus 1 minus z to the power 2k is equal to summation k goes from 1 to 1006 mod of z to the power 2k minus z to the power 2k minus 2. Right. So we have to find all complex numbers z with modulus 1 which satisfy this. Right. So the first step here is to recognize that mod z is 1. So when I take mod of z power 2k plus 1 minus z power 2k, I can take z power 2k common. And this is mod of z minus 1. And this part is 1. So this is simply mod of z minus 1. And if you think about the same thing from the other side, you will be able to say that mod of z power 2k minus z power 2k minus 2 would be z power 2k minus 2 common, and this will be z square minus 1. Okay? And this part is going to be 1. So this is mod of z square minus 1. Right? So now what we have is two questions. This question boils down to this. K is 1 to 1006. This part has all the k terms have actually disappeared and you have z minus 1. And here you have summation k is equal to 1 to 1006. And again you have mod of z square minus 1 and k terms have actually disappeared. Right? So ultimately the summation doesn't matter here. Both the summations are over the same limits. So you will get 1006 times this is equal to 1006 times this. So ultimately the equation becomes simply this much. Right? And that is a pretty easy equation to solve. So we will say mod of z minus 1 is equal to mod of z square minus 1, which is equal to mod of z minus 1 into mod of z plus 1. And the way you can solve this equation is either mod z minus 1 is 0 or mod z plus 1 is 1, right? So mod of z minus 1 is equal to 0 gives us z must be 1, right? And here what we get is mod of z plus 1 is 1 means we also know that mod of z is 1. So we know mod of z square is 1. So we know z into z conjugate is 1. So z conjugate is 1 by z. All of this stuff is already known to us, and let's try to solve this equation then. So what we do is we square it and we write it as z plus 1, z conjugate plus 1 equals 1. And we get mod z square plus z conjugate plus 1 is equal to 1. And we get this is 1 plus z plus 1 by z plus 1 equals 1. So we get basically z plus 1 by z is equal to minus 1, right? Basically now we solve it using a quadratic formula. We get z square plus z plus 1 is equal to 0 after taking common LCM and so on. You can solve it to get z is equal to minus 1 plus minus I root 3 by 2. And these both of these complex numbers satisfy the condition that mod z is 1. So our final answer will have three answers. Z could be 1 and it could be minus 1 plus minus I root 3 by 2. These are our answers. This was a pretty straightforward problem, nothing very difficult here. The idea was simply take z power 2k and all common outside, and since mod z is 1, basically you will realize that the equality boils down to a pretty simple equation, right? Okay. In the next video, what we will be discussing is the trigonometric form of complex numbers, and we'll see applications of trigonometric complex numbers in problems involving polynomials. So basically, we'll look at the Euler form in greater detail and also the De Moivre's theorem. As a sample problem, I can show you one simple question, which will be a teaser for the next video. Let's look at this one. Let z is equal to cos 40 degrees plus I sine 40 degrees. Find the value of mod of z plus 2z square, this pattern 9z power 9, whole to the power minus 1. So, okay, so we can say that this z can be written as cos 2 pi by 9 plus I sine 2 pi by 9. And therefore, z power 9 is equal to cos 2 pi plus I sine 2 pi by De Moivre's theorem, which is 1. So z power 9 is equal to 1. And if I look at my expression here, a is z plus 2z square plus 3z cube till 9z power 9. This expression, if this is like a AGP. There is a GP term series that is going on, z square, z cube. And there is also an AP, 1 in 2, 3 till 9. So the way to solve this is multiply by the common ratio of the ZP. So ZA, when you multiply, you shift it and write it like this, z square plus 2z cube. And this will be 8z power 9 plus 9z power 10. And then we subtract it. You get 1 minus z times a is equal to here z plus z square till z power 9 minus 9z power 10, right? Now think about it. Since z power 9 is 1, z power 10 is z. So this is basically sum of z plus z square till z power 9 minus 9z, right? And what is the summation of this GP series? So let's write that on the next screen. We have 1 minus z times a is equal to the summation of that GP will become Let me just write the series first. It was z plus z squared till z power 9 minus 9z, and this series is z into 1 plus z till z power 8. There are 9 terms overall, so this is z power 9 minus 1 by z minus 1. There was a minus 9z here, so minus 9z. We have 1 minus z times a is equal to this, right? So what we can do is we can find the value of a by simplifying this expression. What do we get when we simplify? Let's see. Also remember that z power 9 was 1 actually. So that helps us a lot, because this means that this term will become 0. Because z power 9 is 1, so numerator is 0. We get minus 9z here. So that means a is equal to minus 9z by 1 minus z. So it is 9z by z minus 1. So a is this. So mod of a is equal to mod of 9z by mod of z minus 1. And that was basically mod of 9z is going to be 9 times mod of z, which is 9 by mod of z minus 1, right? So now all we have to do is find the mod of z minus 1. And remember, z was cos 2 pi by 9 plus I sine 2 pi by 9. So what is mod of z minus 1? Z minus 1 can be written as cos 2 pi by 9 minus 1 plus I sine 2 pi by 9. And this can be simplified as basically 1 minus 2. So minus 2 sine square pi by 9 plus 2I sine pi by 9 cos pi by 9. You can take 2 sine pi by 9 common and you get a minus sine pi by 9 plus I cos pi by 9. This is your z minus 1. When you take mod, this term will have modulus of 1. The modulus of the overall z minus 1 is coming as 2 sine pi by 9, right? So my modulus of a is equal to 9 by 2 sine pi by 9 is 20 degrees. So what we wanted to find was a inverse. So that is going to be 2 by 9 sine 20 degrees. That is your answer, 2 by 9 sine 20 degrees. So again, here we learned some new tricks. The basic idea was De Moivre's theorem and how to apply powers of complex numbers, how to handle those. If you need a basic intro to this topic, you should consult some of the videos that I have already shared in my previous courses on the channel. Like I have a lot of complex number videos on the channel, so you can look at it if you're not familiar with the basics. The part of the course that we are currently doing right now will cover only problems. So I want to discuss whatever theory is required, but do it by solving problems. So in the next class, we'll continue with slightly harder problems, and we'll see how complex numbers are applied in contexts where polynomials are present. How we'll use both of those concepts together, right? So stay tuned for the next video of the series. I hope you have learned something from this one, and there will be more problems on complex numbers coming up in the next few videos in this particular section of the course. So I'll see you next time. Hope you have learned something from this video. If you like the content, please subscribe to the channel, like the videos, and share it with your friends. Your support is absolutely essential for me to continue providing content like this. I'll see you in the next class.